Thank you very much, Neda, for this very nice invitation to this webinar. It is a real pleasure to deliver it and to see all friends and colleagues. And I hope that this tradition continues. Of course, I also hope that things will improve in the future and that we can meet in person anytime soon. But for the time being, this is actually a very nice replacement for these face-to-face meetings. So it is my pleasure and I appreciate this invitation. So with this, let me start with the talk. As Neda mentioned, this is an attempt to introduce from the field theoretical point of view, a calculation that can be compared to experimental data and that could perhaps indicate the presence of strong magnetic fields in peripheral heavy ion collisions. The attempts so far, as you may imagine, have not been that successful. In other words, hints of the presence of magnetic fields in heavy ion collisions from the point of view of charge segregation have not yet been confirmed. In fact, there are too many problems with this kind of observable. So it is actually a very nice and well, a problem which is in the mind of people that are trying to connect these theoretical developments with observables. And so finding an observable that is linked to the presence of these magnetic fields could be very interesting. So this is the case for today's talk. And what I want to call your attention is that perhaps the presence of magnetic fields in very early stages of the collision could be probed by the production of photons, so as to try to explain the so-called direct photon puzzle. So the overview for the talk is listed here. I'll first make a long introduction to what we understand is the direct photon puzzle, to then proceed to try to find why magnetic fields present in peripheral heavy ion collisions may have some bearings on explaining this puzzle. The specific calculation on which this seminar is based on is the gluon fusion splitting mechanism, which is a channel that is that can be opened by the presence of these magnetic fields. And then what I'll do is to show our explicit calculation. What we did was to use URQMD to simulate heavy ion collisions and to compute two important observables, the lifetime evolution of the magnetic field and the reaction volume, which, as you will see, are important pieces for the description of this yield and V2, photon V2. Then I'll go on and present the results for the excess photon yield and elliptic flow, and I'll conclude. Of course, as Neda mentioned, please, if you feel so, you can interrupt me anytime you want to clarify anything. We have plenty of time, as Neda mentioned. So let me just go ahead and make a brief summary of why the study of direct photons is interesting. First of all, as you all know, it's an excellent probe to understand the time evolution of the hot and dense matter created in heavy ion collisions at ultra-relativistic energies. These photons are produced throughout the collision in every one of the stages. And because they interact only electromagnetically, they carry information about the medium at any time these were produced. And when they are produced through the interactions at the partonic or hadronic levels, they are produced through scatterings, and these are called the direct photons. In other words, by definition, these are not photons that come from hadronic decays, but rather from direct interactions. In particular, what are known as thermal photons contribute apparently dominantly at low momentum, and of course are a very important probe, for instance, to determine the temperature at the very early stages. As I'll mention later, my personal point of view is that we can perhaps question this wording, in the sense that even though experiments extract the early temperature from fitting an exponentially decaying function in the photon spectrum, it may be too well, it may be rushing or pushing it a little bit to try to extract a temperature from such a procedure. Nevertheless, this is the current understanding of the spectra, but we of course can discuss about the features of this spectra. So can you please move on? Thank you. So having said this, let me show you what has been measured. And what I'm showing you here is the recent, or the most recent PHENIX data showing the yield of photons for a number of colliding systems at different energies and centralities. So from left to right, you see for gold-gold collisions at two different energies and basically minimum bias collisions. You can also see proton-proton collisions at two different energies. And the data is contrasted to PQCD calculations, also performed at two different energies. What you can see from this data is that, and the comparison to the theoretical calculations, is that PQCD does a very good job describing the spectrum for large PT, and I will say that larger than perhaps 3 GeVs is what I call large. But for small PT, you can see that the gold-gold collision systems are not well described by PQCD, and in fact, they don't follow the trend that the data follows at larger PT. In the middle of this slide, the middle panel, what you can see is different centrality bins for a single energy in gold-gold collisions, also PP collisions at the highest rHIC energy, also contrasted with with theoretical calculations. Now, you can see that for these different centrality bins, the same trend is being observed. In other words, PQCD does a very good job for large PT, whereas at low PT, PQCD is not appropriate. Now, you can also do the same, play the same game with Alice data. For instance, in the rightmost panel, you can see lead-lead collisions at two TeVs, and this is for central events in Alice. And as you can see, the same can be said. PQCD does a very good job at large PT, whereas at low PT, it doesn't. So what we can conclude is that for high PT photons, you can imagine that they come from hard scatterings, and therefore PQCD does a very good job. Whereas for low PT photons, it seems that there is something else going on. STAR associates this behavior to a thermal behavior. So let us move on to the next transparency. Thank you. So these can also be shown in a different way, or slightly different way, where what you see is the ratio of direct photons to inclusive photons. So you see that from left to right, you move from small systems, PP, at high energy, square root of SNN equal to 200 GeVs, also central rapidities, to small large system, also minimum bias, and then to two large systems, copper-copper and gold-gold minimum bias, both. So you see that in small systems, PP, PQCD calculations, which are these lines, green, blue, and red, which differ from each other only by what is the cutoff, low momentum cutoff that they include in their calculations. But nevertheless, PQCD does a very good job. They describe this ratio quite well. This is not necessarily the case, although the description seems to be reasonable for deuteron-gold collisions, minimum bias. But it definitely does not make a good job for large systems. So this is another way to say that direct photons have something else than just a superposition of PQCD PP collisions. Next, please. Now, why is this a puzzle? Well, the reason why this is a puzzle is that if you compare both the yield, the elliptic flow, and the rAA for these photons with the state-of-the-art hydro calculations that include basically all of the physics that is successful describing other observables, such as, for instance, dileptons, which is something important to mention because, well, dileptons and photons are cousins from each other. So you see that these state-of-the-art calculations do not reproduce or are slightly below, so to speak, the experimental yield. So this is exemplified, for instance, in the leftmost panel of this transparency, where you can see that in central collisions, gold-gold at rHIC, the state-of-the-art calculations do not reproduce, are slightly below data. And the same can be said, for instance, for V2, which is shown in the middle panel. Data are above the calculations, and also rAA. rAA seems to be also below within experimental, well, in this case, systematic uncertainties, but nevertheless below the central points. Next, please. So, as I mentioned, the prompt photons come from the interactions either at the partonic or the hadronic level, and they are produced in these direct interactions. And as you can see, this is just to reiterate, PHENIX data is above the PQCD calculation scale with the number of collisions. Next, please. So what is it involved in the calculation? Well, it's everything that produces photons, including the non-cocktail, that is to speak, to say the prompt ones, the direct ones. So these are the prompts, the thermal, if they come from thermal processes, and the non-cocktail. So all of these are hereby summarized, and I'm not going to go into detail. Yeah, as a matter of fact, I'm not familiar with all of these calculations, but nevertheless, what I want you to notice is that pretty much everything that is known and that works for other observables is thrown at this calculation, and still the computation is not in say, excellent agreement with the data. Next, please. Well, this is true for the for energies at rHIC, but perhaps it's not that fair for Alice energies. So, for instance, in the right panel of this transparency, you can see data on lead that contains all of the ingredients in these calculations compared to their data, to Alice data. And as you can see, the description is much better, although still in the low part of the error bars, so to speak. This is not true with the same ingredients for PHENIX data, which is shown in the left panel. So what we can draw from this transparency is that although the description that PHENIX energies is not that good, it improves when it comes to Alice data, that is LHC energies. Now, this is something important to bear in mind. The question that perhaps one wants to keep pursuing or pushing, especially for the best two energy scanning program, that is run is what happens at smaller energies. In other words, does the calculation become better, or the discrepancies are larger? This is also a very nice question for Nika energies, which will be probing deep into the effective, I'm sorry, the QCD phase diagram. So next, please. The same can be said for V2. So for photons which are do not have a thermal component, the description in the right panels, you see the red lines, they are not very good, so to speak. When you include the effect of the thermal effects, the agreement improves, both for PHENIX and ALICE. And the left panel is just shown for comparison to show that the yield is also well described in ALICE. So it seems that something like a thermal component is needed to study or to try to, to understand the V2 as well. So next, please. Let me come to a summary of what I just showed you in terms of what is known for experimental data. So PHENIX has found that in the collision of large systems at different centralities and beam energies, large energies, the yield of low PT photons, this is actually that I didn't show, but you can take my word for this. It scales with a given power of n, the number of collisions, which suggests that these photons, that the source of these photons is very similar for different beam energies and colliding species, force for large species. Photon V2 is as large as that of pions. This is still puzzling because since V2 for pions is attributed to flow, and it takes time to build flow, it is not clear whether direct photons, the V2 from photons comes from from flow, which develops at later stages of the collision. Even more if the temperature that can be extracted from the yield is attributed to the early stages. So this is still puzzling, and both pictures are not really reconciled. So, of course, there are some improvements with the description of ALICE and PHENIX data, because, of course, hydrodynamic and transport calculations are always being improved. And however, I think it's fair to say that the agreement is not yet complete. Next, please. So after this long introduction, which I thought it was important to try to put into context what is the current understanding of the experimental data, let me come to try to introduce a possibility that is being pursued, I should say, from some time ago already, but I think that in recent times it's getting closer to have strong, robust predictions for the observables, such as the yield and V2. And this is the presence, the possible presence of magnetic fields which are generated in peripheral heavy ion collisions. Next. So as an example, let me just show you an old calculation from these colleagues, Skokov and Toniev, Ilarionov, for the strength of the magnetic field in units of the pion mass squared as a function of time in Fermis for two different colliding systems. Well, no, same colliding system gold and gold at a given impact parameter for Fermis, and for two different collision energies, 130 and 200 GeVs. So you can see that this, the strength of this magnetic field is, well, is appreciable. In other words, it is comparable to the square of the pion mass. In this calculation for the largest energy, it even reaches twice the pion mass squared. But the lifetime is very small, it's short actually. And you can say that it is not larger than perhaps 0.2 Fermis. So now you can start thinking, well, is it true that these photons, if they were produced during the times when the magnetic field was appreciable, is it really true that there are some thermal effects already present in the collision region to try to describe the photons, the photon yield and V2 from a combination of magnetic and thermal effects? Well, it could be. I mean, it's true that well, hydro calculations need a very early time to be, especially at large energies, to start the hydro revolution, that is. Perhaps it's not these early times, but nevertheless, it could be. It's something that one could explore, of course. My personal point of view is that it is difficult to have thermal effects. Nevertheless, and I'm glad that Igor is here, because perhaps this will give rise to lively discussions. Next, please. You will see that Igor and collaborators have recently made a description of thermal and magnetic effects, starting from the photon polarization tensor, and in particular from the imaginary part of it, so as to extract all of the possible sources of photons coming from this sort of diagram, or this diagram, in the presence of a magnetic field. I remind you that these mechanisms are not, wouldn't produce photons in the absence of a magnetic field, but in the presence of a magnetic field, these channels are open. Next, please. An interesting result from this calculation is that V2 has a large strength for large, well, for, that is, in the rightmost part of this KT. However, an intriguing result is that V2 becomes negative for the smallest energies, or the smallest momenta. So I should say I read the paper, I am interested on following it up, but I don't understand this behavior. I need to be to follow through with more detail, but still it is intriguing to say the least. Next, please. So there are, of course, other ways of incorporating the effects of magnetic fields into the yield or V2 of photons that may be produced by the presence of these fields. Some of them include the thermal effects, some of them don't. Let me just here concentrate on a recent calculation that we put forward, which actually follows after another calculation that we also published 1 year ago, 2 years ago maybe, which was done by this team of collaborators, one student, soon to graduate and looking for postdocs, Jorge Castaño, and two colleagues, Isabel Dominguez and Marilena Tejeda, and a master's student who's actually now, well, he was a master's student by then. Now he's pursuing his PhD in Urbana-Champaign, working with Jorge Noroña. This work is published in this reference, and the idea is that what we wanted to do is to study the low PT photon production from processes which are allowed by the presence of strong magnetic fields, and at the very early stages of a heavy ion collision, peripheral heavy ion collision, which do not necessarily need to include thermal effects, but that may or need to account for the large presence of glue. In other words, short after the Glassma shatters, you have lots of glue, and the question is, what is the influence of this large amount of gluons in the photon production process? Next, please. And what we studied were these two closely related processes. The left diagrams show what we call the gluon fusion channel. In other words, if you have lots of gluons and you have the presence of a magnetic field, there is this channel which opens up and allows you to fuse two gluons and produce a photon. Now, you can see 6 diagrams here, and I'll try to explain later on what these 6 Feynman diagrams mean. But I guess it's easy to see what this means even from starting now. See, in the left first 2 columns, you see that what you have is the triangle made out of quarks, and these quarks flow. The flow of charge goes in one way, and then say for the first row, it goes in the other way. Of course, those 2 diagrams need to be accounted for in the calculation. One is the charge conjugate of the other, so the complete calculation needs to account for them. And but there is another thing that it may not be easy to see, but let me just address the attention to. There is a double line. This vertical line with momentum R. It indicates that what is needed to be accounted for there, yes, that one, is not the lowest Landau level as it would have been expected if we are carrying out a computation where we want to account for the strong magnetic field. So this actually means the first excited Landau level, whereas the lines without being, the single lines, not the double ones, indeed represent the lowest Landau level. So you have 6 diagrams because, of course, what you need to account for is the fact that the first excited Landau level can be any one of these triangle internal lines. And so once you do that and you account for the complex conjugate of the process, then you have 6 diagrams to account for. The diagrams on the rightmost columns are representing a closely related process. This is what we call the gluon splitting. In other words, a gluon comes in and then it splits, and it splits into a photon and another gluon. Of course, one and the other are related by the crossing symmetry. That is, the left columns and the right columns are related to each other using crossing symmetry. So these 2 processes need to be accounted for in order to extract the overall photon yield. Next, please. So what are the ingredients to compute these diagrams? As you can see, or at least it may be just me, but when I started thinking about this calculation, I got scared, of course. And so the reason why I got scared is that you can imagine that it's not easy to carry out these calculations. Whenever a triangle is involved, it's well, not bad news though, but it's at least scary news. So one needs to try to have in mind all of the possible general aspects that go into the calculation. So let me try to outline some of them, because I believe that even in terms of theoretical grounds, the calculation of these diagrams, of course, they are motivated by our search for observables that are related to magnetic fields in heavy ion collisions. But theoretically, I think that they are interesting on their own. And the first observation that needs to be accounted for is that the external particles, gluons or photons, move along the light cone. This is actually something that may have not been expected. In other words, you can always compute the real part of the photon or gluon self-energy in the presence of a magnetic field, which is the bubble diagram that Igor computed, by the way. But if you want the dispersion relation, and you compute it to all orders in the external magnetic field, it is not easy, it's numerically challenging, but you can prove that the gluons keep moving along the light cone. In other words, there is no change to the dispersion properties of gluons or photons. This is a bit unexpected because you see, even though these are neutral particles, there is no a priori reason why you should expect that the magnetized medium does not affect the dispersion properties. What I mean is that even though there are channels which indicate what are the polarization states which are not the same as the vacuum polarization states, still in each one of these polarization states, gluons and photons move along the light cone. This, as I said, is a little bit unexpected. It is discussed in more detail in this reference that I'm showing you here, which was just put forward in the archives recently. Now, second, because the magnetic field is constant and spatially uniform, it cannot transfer form momentum to the gluons or the photons. So their form momenta are conserved by themselves. In other words, if they move along the light cone, you can always extract the energy out of the form vector, and the energy momentum conservation equation can be written in the manner that I'm showing here in this first of these equations in the middle. So you see that the problem reduces a little bit because what you need to account for is the energy and the direction of motion. But as you see, motion along the light cone and energy momentum conservation can only be satisfied together if gluons move. Well, actually, not only gluons and photons move along the same direction. It's the only way you can satisfy these conditions. So the three particles propagate in the same direction. And for instance, for gluon fusion, this means that if you have your observable is Q, the photon's momentum, then the momentum of both gluons, P and K, are related to Q in the manner that I'm showing here. So this is actually a relevant observation because then the calculation becomes a bit less complicated, so to speak. The other part of the calculation is when you compute the matrix element, of course, you have the breaking of Lorentz invariance. And that means that you need to account for the Schwinger phase, and I'm going to be working in the Schwinger proper time formalism. So the Schwinger phase needs to be accounted for in these triangles. Now, interestingly enough, the calculation, which at first sight, or at least it happened to me at first sight, may have introduced some doubts about conservation of momentum in the transverse direction, transverse to the direction of the magnetic field, actually shows that conservation of energy momentum is fulfilled, provided, of course, that the motion of the external particles, in this case, photons, gluons, which are not electrically charged, can be described by plane waves. In other words, that the motion is not affected by the presence of the magnetic field. Now, you could think that this is natural, particularly if the medium effects do not affect the dispersion property, that is the motion of the modes, that the eigenmodes in the presence of the magnetic fields. In other words, that the gluons and photons move along the light cone. But this is non-trivial if you were treating charged particles as external particles, which happens everywhere else in other calculations. So you can have quarks, you can have electrons as external particles. They are electrically charged, and therefore you could think that this description cannot be accomplished, and therefore that energy momentum conservation for asymptotically propagating particles, charged particles, is not going to be satisfied. However, you can always separate the problem into what you want to describe at the short distances. In other words, how this vertex function is modified from long distance propagation, which is something that can be factored out. When you want to look for short distance behavior, it is a good approximation to think that even charged particles are born into plane wave states. And if you do that, then, as we show in the reference that is listed here at the beginning of this transparency, it is also true that you can factor out energy momentum conservation from your process. Next. So this is the process. This is one of them. This is the gluon fusion matrix element. As you can see, it has all of the necessary ingredients. It has the plane wave motion of the external particles, which are at each vertex, which I represent by the letters X, Y, and Z. These are the space-time position of the vertices. These vertices are coupled to the external momentum, and the motion of the internal particles is of course also represented by plane waves. It's written here in this second row. And you have to integrate over internal momenta and all of the possible positions of the vertices of these triangles. And what you need to do is to consider the triangles going in one and the other direction, of course. And there are the Schringer phases and the wave functions for the external vector particles, gluons or photon. And you have to add the complex conjugate, and then you need to crank the wheel and try to get to some sensible result. Next, please. Now, in order to represent the motion of the particles in the loop, you need to use the Schringer propagator for charged particles in the presence of a magnetic field. As you know, this can be written as a phase factor, which contains the translationally, the breaking of the translational invariance, and the piece which is actually translationally invariant, which is the Fourier transform of the propagator in the presence of a magnetic field as a function of the particle's momentum. And this is given explicitly by this expression in the second row, where the phase factor is given by the third row. So you see, if you wanted to do the calculation to all orders in the magnetic field, this would be the ingredient that you need to use. However, you can imagine that this is, well, difficult, to say the least. So we need to resort to an approximation. And next, please.
Sorry, Alejandro.
Yes, yes.
So Igor has a question.
Yes, please, Igor.
I think Igor.
Yeah, the quick question I have is that amplitude you wrote seemed to be of order E G squared, or if you calculate the actual process, it will be alpha S squared. Is that correct?
That's correct, yes.
But that seemed to be so much more suppressed than the standard 2-to-2 processes like work gluon into Photon work. That seemed to be only alpha S. So it should be dominant, not this process, isn't it right?
Right, that's true. However, as you'll see, there is also an enhancement coming from the fact that the magnetic field is large. But let us come, yeah, your observation is correct. This is a process which is not necessarily dominant, but it's certainly there. It is my impression. So it was worthwhile computing it. But yeah, you're right. There is a suppression coming from factors of the couplings, but there's also an enhancement coming from the large magnetic field strength. True.
Okay, sounds good.
Thank you.
Thank you.
So we want to do this computation, as I mentioned, having in mind that the process happens at early times, where my personal bias, so to speak, this, of course, there is no proof of this, nobody knows. But my personal bias is that thermalization has not had time yet to kick in. And therefore, in terms of the energy scales present in the problem, the magnetic field strength is the dominant one. Now, let us put together also an extra ingredient, which is the fact that these photons, at this, if this is the case, then at these stages, there is an extra ingredient. This ingredient is the large abundance of gluons, which are not yet thermalized, but they come from the low momentum part of the partons that collide with each other during the heavy ion collision. This is what we call the shattered plasma. So in other words, before these nuclei collide, they are made out, especially at large energies, of this so-called Glassma. But when the nuclei collide, the Glassma comes, or there is energy to bring about these gluons into being, well, real objects, real in the sense that they can propagate. So if that is the case, then the ingredient that needs to be accounted for together with the large magnetic field is this large abundance of gluons. Now, one more thing to keep in mind is that because the quark masses, at least the ones that are relevant for this calculation, the light ones, is so small, and the magnetic field is large. So we could think that we can ignore the fermion mass, the quark mass, and consider that, as I said, the largest energy scale is the magnetic field. So because of that, we want to work in the lowest Landau level approximation, except that, as I pointed out too, when you do the calculation with these triangles and all of the quarks are in the LLL, the diagrams cancel. So in order to have a non-vanishing amplitude, you need that at least one of these quarks is in the first Landau level state. This is easy to show. Well, easy. It can be shown rather easily once you've done the calculation. I guess I was trying to look for a more physical explanation. I couldn't come up with this explanation. I'm still thinking on this, but of course it should be present there very easily. Maybe some of you in the audience knows the answer, but the fact is that you need that at least one of these quarks is in the first Landau level, as opposed to the lowest Landau level. Next, please.
Okay, I think there's another question by Masoud.
Yes, Masoud.
Who has no hand, no microphone.
Go ahead.
Okay, Masoud. Masoud, do you have any question? Oh.
Oops.
No, I think something is going wrong.
Maybe he's Masoud. Maybe you have your
sorry.
Yes. No.
Sorry. I couldn't find the unmute button.
Oh,
So my question was about, because I can actually was about the energy scale. It's about the energy scale, which is, you say that the magnetic field is a dominant energy scale. But when we look at the works that are about the LD times, they use something like an effective temperature, which is roughly equal to the Gluon momentum saturation scale.
correct.
Okay.
Correct.
So that's this is I guess I can guess that one should compare EB to Q squared. Yeah.
Right. This is a very good observation. Maybe I interrupted you. Please go ahead.
No, that's my question.
Right. Yes. What I have in mind, what we have in mind, is see, you have. Let me put them this way. You have dynamical energy scales. Dynamical in the sense that they go into the dynamics of the process. In other words, we are computing the matrix element squared for this process. So everything that is involved there is dynamical in that sense. It's the dynamics of the quantum process, so to speak. So the only thing that is involved in the dynamics are the magnetic field strength, the quark mass, and the external momenta. That's the only dynamics. This is the only thing that is involved in the matrix element calculation. Now, to bring this calculation into light, in other words, to put in the ingredient of the large abundance of glue in the process, then you need to put an extra factor, which is external to the dynamics. And this is the occupation number. So one can model the occupation number for the shattered Glassma in a different number of ways. And one of them, and actually we resort to that, is to mimic the occupation number by some sort of a occupation number Bose-Einstein-like occupation number, where you need to introduce some sort of a temperature, so to speak, which is related to the saturation scale. And this is large. This is of order 1 or 2 GeVs. But this is external. In other words, this is the occupation number, and it accounts for the quantum statistics, not for the quantum dynamics, which comes into the matrix element calculation. This is why, for the computation of the matrix element, I'm separating the scales in the way I described. When I come back to put in the information of the large occupation number, this energy scale is large, but it's external. It accounts for the statistics, so to speak, of the process. I don't know if I answered your question.
Thanks. Yes, I'm convinced.
Okay, thank you very much.
Okay, I think there is another question by Efren.
Please,
Yes.
Efren.
So Efren.
Alejandro, it's about the same kind of question, no? Because it's not clear for me. I see that it seems that for you to have a high occupation of the lowest Landau level will be important. Because if not...
Not necessarily high occupation of the lowest Landau level. It is the calculation for the matrix is done using LLL and 1LL. And then once you have
I mean the
moment of the gluons will be weighed by an occupation number, true.
Well, if you need, that's what is not totally clear for me, but if you need to have a high occupation of the first Landau levels, not to have an effect, because the question will be, what is the physics behind what you are doing, not why it will be important. And it will be important if the magnetic field is very high, because then you can only consider the lowest Landau level. But in this case, I think that the temperature will be playing a very important role to decrease the population, you know, because even if you take into account the equipartition of energy, you will expect that T squared have to be of the order of B. Why?
Okay, let me try to, yes, sorry, go ahead. Let me try to be clearer, because maybe I induced you to some misunderstanding. You see, what I'm saying, Masoud, can you go back 1 or 2 transparencies? One more. All the way to the diagrams, actually. There. You see, Efrain, what I'm trying to say is that there are 2 pieces of the calculation. One is the matrix element square. And you see, for the matrix element square, what you need, of course, is to compute the triangles. Feynman diagram rules for the triangles, where I need, as I mentioned, that one of the quarks in the triangle is in the first excited Landau level. But see, there is no, here you don't need to weigh these quarks with any occupation number. As a matter of fact, this is just a quantum process, not a statistical one, so to speak. So just do the calculation there, following the usual Feynman rules in the presence of a magnetic field. But when you square this matrix element and you put it into the context of a yield, then what you need to do is to weigh this matrix element with the occupation number of the external particles, not the photon though. The photon is not assumed to be in thermal equilibrium, no. You get what you get, provided you put the appropriate weight for the gluons in the process. In other words, it is, in order to account for the high occupation number, what you need to do is to put an extra factor and then integrate over phase space. That accounts for the fact that the gluon with label P and the gluon with label K in these diagrams are in states with a high occupation number. So in that sense, there is nothing that these high occupation numbers have to do or to say about the internal triangle, the lines in the internal triangle. Did I make myself clear?
There is a, this calculation is a QFT. You don't have temperature there.
Right, exactly, no temperature. There,
the
temperature, if you wanted, you can put it to the external particles. We decided, we chose not to, because what we want to explore is what happens if you don't have a temperature. Can you do a good...
For the internals.
The internal ones are not. The internal ones is just pure magnetic field, no temperature there.
And what about the diagrams that will come from the thermal part? Because
as I said,
physics has to be there, no? That if you put, so suppose that always I can consider the zero Landau level. But if I have a temperature huge and the magnetic field is too small, then the contribution at the end is very, very small.
Absolutely.
If I am considering the zero Landau level as one of the terms that I will have in the series. Because if the temperature is too high with respect to the magnetic field, the thermal contribution will
dominate.
You know, that's the question.
Absolutely, you're absolutely right. But this happens at later stages of the collision. Remember, we are.
Okay.
So can you go back to the?
That's the physical assumption, no? The physical assumption.
That's the physical assumption.
Okay.
If you can show this. Right, this is early stages. Can you go back, Masoud, to the plots where I showed Skokov's result? There. You see, Efrain, the width of this, the lifetime of this magnetic field is 0.2 Fermis at the most. So there, if you want to account for the presence of the magnetic fields, you better, we forgot about, we don't think that there is temperature at those early stages. In other words, the system hasn't had enough time to thermalize in the way we think about thermalization. That happens for later stages, where the magnetic field is just nothing. You see, it has reduced to zero. So at later stages, you have thermal effects, but you don't have magnetic fields. So this is the point. Now, let me point out to something interesting that may happen at lower energies. We've done preliminary calculations to see what happens at Nika energies, whether the lifetime of the magnetic field is as small as this, and we have found that it increases. The intensity decreases. So for Nika energy, we are talking about 10 GeVs, say. The width increases, but the strength decreases. Now, even if the strength decreases and the width increases, there is still a large presence of a magnetic field at later stages, and perhaps there the temperature has some bearings. But for this setting, so to speak, at large energies, rHIC, LHC, rHIC at top energies, LHC, it seems to us that the temperature is not an ingredient to account for in these triangles. So now, Masoud, can you go back to the triangles? There. So there you only need to account for the propagators without temperature, but in the presence of the magnetic field.
Okay.
Did I explain this?
That you are supposing that the magnetic field will be huge at times
right.
where the temperature is not so big. Because, you know,
exactly.
I remember that times ago when I was trying to do something in this field, always they say that the magnetic field and the temperature were of the same order. And then that was really, you know, not very attractive because of that.
Right. It cannot be. First of all, there is not enough time for for the system to finalize. It isn't. That's my impression. But Igor may disagree with that. So perhaps later we can.
I will, but later.
Yeah, exactly. I could hear him holding his breath. You see, he was heavily breathing, but still containing himself. So later he'll.
I was muted. You couldn't hear.
All right. So let's continue.
Okay.
And
Thank
then,
you for your answer.
Thank you, Efrain. So, well, if you work with this approximation and for massless quarks, you see that the lowest Landau level propagator is the first row here. Since it's just a single level, there is only one possible projection for the spin with respect to the magnetic field direction. And depending on the charge, this projection is given by the last row of this transparency. Whereas if you're working with the first excited, the Landau level, then you have to work with this a little bit more involved propagator, which is labeled as S1. This, of course, includes both projections of the spin of the particle with respect to the direction of the magnetic field. Next, please. So let me just walk you through the calculation, just to not overwhelm you with so many details. What we want to do is to focus on low photon momentum. So in other words, our results are just valid for small photon momentum. Photon momentum has to be small compared to the magnetic field. So that already sets the stage so that our comparison to experimental data is going to be valid only for the lowest part of the spectrum. Then, as I mentioned, momentum is conserved at the vertices. So if you work with small photon momentum, external photon momentum, that translates into the magnitude of momenta in the loop, especially because you need a cutoff given by the magnetic field. So because of that, what we need to do in order to make this, of course, traceable and still interesting enough, is to make an approximation. And the approximation we made was to work with small internal momentum. This is cut off anyway, as I said. And so the internal momenta, which here we call Ts and R, they are squared, especially the parallel part of their square, because this is what gets compared to the magnetic field, are going to be taken as small. Now, we are, of course, restricting ourselves to the small part of the photon spectra, but we are working on relaxing this approximation. Next.
Did you say small or large? Because it says large on the slide.
Sorry, I made a mistake. It's small. The magnetic field is the large quantity here.
So there is a typo in the equation, right?
It's a typo. It's a typo. Yes, I'm sorry. Okay, so well, if we do that, then the calculation is still large, but it's nice, as a matter of fact, because see, you can extract a lot of physics from there, as is shown in this transparency. You see, the matrix element contains the ingredients that we were looking for. We have this energy momentum conservation, which is, I mean, it should be there. And this comes, of course, from our treatment of these particles, either in the loop or the external ones as plane waves. Now, there is, of course, well, the color factors and everything, but these tensor structures are longitudinal. So what it means is that the particles, photons or gluons, are going to be longitudinal. So only longitudinal components of their polarization tensors are to be accounted for in this calculation. But this is born out of the calculation. It's not something that we assumed. So the difficult part of the calculation is, of course, computing explicitly these functions h that I'm showing here. And of course, you just have to do it. Well, these functions h and the function f are the ones that eventually have the information, both on the contribution from transverse pieces, and of course, what goes on in that exponential factor. So as you can see, well, I mean, all of the ingredients are there. Anyway, next. All right, so next, what you need to do is to square the matrix element and account for both processes. So far, what I just said, what I just mentioned was, say, focusing on the gluon fusion diagram, but of course you need to add the gluon splitting diagram. And this is what it's done here. You need to sum over polarizations, initial and final. And of course, for the matrix element squared, what you do is you square the delta function, and one of the factors of that square has to account for the lifetime of the system, which is here represented by V, this math cal V times delta T. So delta T is the lifetime, V is the volume where the process is taking place. And then, as I said, the matrix elements for gluon fusion and gluon splitting are closely related because one is the cross process of the other. And so when you sum up, when you square and sum over polarizations, then you get the same result for both of them, and then both have to be accounted for. You just have to be careful because in one case, the one gluon is in the initial state, the other one is in the final state. Next, please. All right, so then you can put it in, these results, you can put them in to compute the yield. And so you see what you have to do is to integrate over phase space. This is the integration over these variables, P and K. Since momentum is conserved, then the photon momentum is Q is given, well, restricted by this delta function. And this is where we put in the extra piece that I was trying to explain to Efrain and to Masoud explicitly. In other words, you need to account for the occupation number for the gluons. So for the gluon fusion process, these occupation numbers have to account for initial state gluons, whereas for the gluon splitting, one of the factors goes with the initial state and the other one with final state. So there is this Bose-Einstein enhancement. And to make matters simpler, just to simplify matters, our model, so not the dynamical piece, but the piece that goes external with the weight for the statistics of the process, is this occupation number that we borrow from these color glass condensate ideas, these Glassma, shattered Glassma ideas. So there are, of course, parameters involved here. One is eta. Eta is this occupation number. It's got to reflect the fact that you really have a large occupation number. And of course, there is this lambda S, and lambda S is a saturation scale. It's also a large parameter. So eta is a dimensionless parameter. Lambda S is a parameter with dimensions of energy and corresponds to lambda S, the saturation scale. Next, please. The extra ingredient you need is the lifetime and intensity of the magnetic field during its evolution. So for that matter, what we did is to do our own calculation. So we decided to reproduce the results given by previous groups. And we did a calculation. It's a classical calculation. It's based on the use of the linear Wiechert potentials using URQMD. What we want to compute is the width of these distributions and the height, because what we need to do is to evolve in small time intervals the production of photons all over the lifetime of the system. And as you see, the intensity decreases dramatically. So we did the calculation all the way to 1 Fermi, but of course, after 0.2 Fermis, the contribution is rather small. And we use these linear Wiechert potentials, which are represented here. The other ingredient is the volume, how the volume changes with time. And that's shown in the next slide, please. So also using URQMD, we can compute what is the overlap volume for different centralities and a given collision energy and different systems. And this is shown here. You can see that the increase of volume is basically linear. So we compute this volume using the number of participants in the collision, which we extract from URQMD, and the radius of the overlapping nuclei. Well, the increase, as I said, there is linear. It's only 2/3 as opposed to 1/3 because it's the overlap is in 2 directions. Next, please. And here are the results. So here I'm going to show you what we obtained first without comparing to experimental data, just to show you that we have control both for the yield and the V2 coming from magnetic fields. Now, at the end, I'll show you that the V2 from magnetic fields has to be summed to the V2 coming from other sources in a weighted manner. You cannot just show the magnetic field standing alone, the V2 from magnetic fields. You need to weight the average, make a weight average. But anyway, so this is the yield in the left-hand side, and this is computed for gold, or copper using URQMD for different centralities. And the same happens in the right panel for V2. And this is the case when only we use the spectators to produce the magnetic field. As you know, the spectators do not scatter from each other, so they just serve as charged currents that move away from each other, and they produce a magnetic field in the interaction region. So if you now use also spectators and participants, and this is done in the next, please, next transparency, then the same calculation you can do with the magnetic field produced by participants and spectators, and this is the result. It is not very enlightening, so to speak, until you compare to data. So this is done next, please. And here we have it. So we put all of the ingredients together. The calculation of a matrix element at early times, which required the use of magnetic field propagators for the quarks, both in the lowest Landau level and the first excited Landau level. The matrix element squared, both processes, gluon fusion and gluon splitting, weight with the appropriate factors which resemble Bose-Einstein distributions with a high occupation number, and the introduction of the saturation scale. And the results are shown here, first for spectators, only spectators. So the open squares are data from direct photons from PHENIX, 0 to 20% centrality. And our calculation shows gold-gold collisions at the same energy, spectators at the same centrality. So you see that for these central events, the calculation in the left panel is not doing the best job as possible, whereas it becomes better, at least for the low part of the spectrum, becomes better for non-central collisions. This is to be expected if what we're, the photons that we are producing come from a situation in which you have a magnetic field. Now, I have to caution you in this comparison. What we did here, all along what I described to you, was the calculation of the photon yield and V2 coming from what we call an excess of photons. In other words, these are just photons coming from a single process where magnetic fields are involved. So in order to compare to the data, what we need to do is to take the data as it is from PHENIX and subtract everything that is known from the state-of-the-art calculations in the field that account for photons. This, what we took was the result from Paquette et al. which is given in this reference. And so the PHENIX data we subtracted this calculation, and then this is what we are comparing. In other words, we are comparing the the data represents the excess yield, and what we want to attribute, what we want to do is to attribute that excess yield to our calculation. So you see that our calculation does better for this excess yield when we compare to collisions which are non-central. Next, please. You can do the same, play the same game now with the magnetic field coming from participants and spectators. And you see that, well, this makes a better job for even for central collisions, although of course there is a discrepancy, but it does a much better job for the low part of the spectrum in semi-central collisions. Next. And the same can be done for V2. So this is done in these two panels. In the first one, what we do is to compute only the V2 coming from the magnetic field of the spectators. For this calculation, and the right-hand side is for spectators and participants. In both cases, we are only looking at collisions with given centrality bin of corresponding to semi-central collisions, and the full circles correspond to our QMD, our QMD calculations. You see that the data, which is the symbols with the error bars, are well reproduced by our calculation in the low part of the spectrum. Also, our V2 doesn't go, but it seems to go either to 0 or to a very small value, finite value. It doesn't go below 0. So this is, of course, what I mentioned before. What you need to do is to average, a weighted average of the V2, because you cannot just compare to experimental data if you don't do that. So I think that the properties of this V2 are all right. Of course, it is expected that we cannot go or describe the data for larger values of the transverse momentum. And so this is why the discrepancy for those values, say starting from 1.5 GeVs on, the comparison is not good with experimental data. Nevertheless, I think that for small values of the transverse momentum seems to be all right, particularly if you believe the data trend where the V2 does not necessarily go to 0 if you extrapolate. Anyway, so this is an interesting feature of this calculation. And with this, let me go to the conclusions. Yes. So I hope that I could convince you that if you account for the presence of intense magnetic fields during the very early stages of a heavy ion collision, you could set up a calculation in which, without the need of resorting to a thermal component, you could at least describe in a reasonable manner the excess yield of photons as measured in heavy ion collisions. The ingredients, of course, require a high occupation number for gluons during these early stages. So in other words, both things go hand with hand. In other words, large amount of glue together with large magnetic fields. And what we did was to use URQMD calculations to compute the time evolution of both the intensity of magnetic field and the volume. And the photon yield and elliptic flow excess is better described when the field effects at semi-central collisions for heavy systems is described, especially at low energy collisions. So for the future, as I mentioned, we want to relax some of the approximations in the matrix element computation, and anyway, explore perhaps for lower collision energies whether or not thermal effects may be important. And with this, I thank you all for this attention. Thank again, Neda, for this kind invitation, and I'm open to questions.
Okay, thank you very much for this very nice talk. And I guess there are some questions. I think Efrans. Okay, Igor, please.
Yeah, I'm muting myself. Alejandro, the first thing I am a bit confused is the energy momentum conservation. The way you're writing it, for example, on page, what was it, 24, there was this delta function, q minus k minus p. So essentially, the way I read it and the way you said, those are all three massless particles which are on the light cone. That four-dimensional delta function seemed to be completely inconsistent. It should give you 0 unless all the momenta are collinear. Isn't that right? How can you get something non-zero?
As I said, if you can go, Masoud, can you go back some slides? Let me stop you when I see what I want to show. More. There, no. Forward.
Yes, here.
Forward. One more. There.
Mm-hmm.
Yes. What I said is Q needs to be equal to P plus K, which is that delta function that I showed you.
Mm-hmm.
So there is no other way. And moreover, P, Q, and K need to be collinear. There is no other way because this is the
But
only
this is essentially zero phase space for any production.
No. Why? So what you need is some for a given Q. What you need to do is to pick the glue, for instance, for gluon fusion, pick the glue that has P and the other glue that has K, such that P plus K gives you Q.
Right, but P and K should be exactly parallel.
Right.
Unless, exactly parallel. Otherwise, this is zero phase space. But that is a very, very limited phase space when P and K are parallel.
Absolutely, and that is accounted for in this phase space integration. Whatever it is, it's small, large, or tiny, or whatever. It's accounted for in that phase space integration. Can you, Masoud? Can you go forward to the expression with the delta function more? Oh, there.
Essentially, it's Q0 equals K0 plus P0, and K and P should be exactly parallel. That's the only option, which seemed to be should reduce greatly the final contribution. It should be strongly suppressed, it seems.
Igor, I'm telling you, yeah, I agree with you. Can you go a little bit forward, Masoud? One more. There. I'm telling you, yes, of course, you need to enforce that with this phase space integration. It'll give you what it gives you. It's not overcounting, undercounting, nothing. It is just there. Whatever suppression you want it, that is comes out from these kinematical restrictions is accounted for in this.
Okay. Let's assume that this is the case and it's fine for now. But there is another thing that is actually very nicely on this page specifically. You have the distribution of the gluons, which are having characteristic energies of order lambda s. Isn't that right?
Right.
That will be the typical energy of gluons that contributing to this process.
Right, because they come from the static Glassma. Sure.
In a way, that means that when you are considering the amplitude m gamma to gamma, mg to gamma g, then essentially it means that effective triangle becomes like an effective coupling, which is a let's say a short range coupling compared to the characteristic in and out momenta. For the photons, you said that the momenta will be much smaller than magnetic field. Right. That means it's fine for now, but it's kind of seemed to be inconsistent because the characteristic momenta for the glue is actually much larger than that, which suggests to me that what you have to do is to take glue going one way and the other way and essentially nearly exactly compensating each other to give you a very small photon momentum in the out state. And it would be all fine, but this effective coupling, the amplitude that you're calculating, will not be a short range coupling compared to alpha S scale, Compared to alpha S scale, magnetic field is still much smaller, and that seemed to be contradicting to the assumption that only the lowest Landau level contributes.
Not sure about what you're saying. I mean, not sure if I totally agree with what you're saying, but see, let me just, and I try to put everything on top of the table, so to speak. In other words, there is the need of approximations in these calculations in order for you to have a reasonable grasp on what's going on. It's not a trivial calculation as you could imagine. Now, can you, Masoud, go back a little bit? I'll stop you when I see what I want to show you there. No, one more forward. Forward. There. Okay, see, no, one less. The previous one, please. There. You see, part of the yeah, that one, that's excellent. Part of the, so to speak, problem, not problem though, but something that gives you confidence that at least something is captured by this approximation, although not necessarily the full kinematical regime of applicability, is this structure. In other words, it's not easy to show that the matrix element is totally longitudinal with respect to the magnetic field, and this is signaled by these structures that I'm telling you. So at least some part of gauge invariance is being respected. This is actually encouraging. Of course, the kinematical regime where these functions h and f, which are the other ingredients that come out from the calculation, should be computed, may not be the final story. And as a matter of fact, as I mentioned, we are trying to relax those approximations. I understand that it is an approximation which may not capture the whole picture. And how it is correct, this expression is corrected when you try to capture a broader part of the phase space, it is still under computation. Let me put it this way, Igor, I completely agree with you. I wouldn't say it's inconsistent in the sense that you can capture the main feature, which is non-trivial though. This gauge invariance of this matrix element is non-trivial. But indeed, the functions that capture the kinematics may be better computed, and we are trying to do a better job in that respect.
Well, the only suggestion that I'm saying is that you absolutely have to include all Landau levels. That's basically my bottom line I was driving at. And the reason is like this, that triangle diagram, if you are treating it...
Igor, be my guest.
In the spirit of effective theory. No. It is important because it's about consistency. If you treat that triangle diagram as in the spirit of effective theory, then essentially it's only sort of like a separate extra effective coupling only in the case when all external lines are actually having much smaller momenta than all the inside momenta running in the loop. No, not only photon momenta, but all momenta external lines should be smaller.
I think that, no. I think that you're mixing two things. We can keep talking about this later. Maybe some other colleagues have other questions, but I think you're mixing two things. It is not necessary to use all Landau levels. This is not the point. The point that you perhaps are referring to is that within this approximation of large magnetic field, it is necessary to account for all of the momentum range of both the internal and the external particles. And of course, this is completely true. There is nobody will tell you that this is not true. And what I'm trying to tell you is that we resorted to some approximation that still has some information which is at least consistent with gauge invariance. But indeed, it has to be complemented, supplemented with a better assumption about what is the kinematical range of the variables. Completely agree. What I don't agree with is that you need to do all Landau level calculation, especially because what you know is that for large magnetic fields, this is not a bad approximation. As a matter of fact, done extensive studies on showing that.
Disagree. It's terrible approximation when you have the characteristic external lines with large momenta. In fact, in our case, even temperatures of the order of several hundred MeV is already making it bad. And you are taking lambda s, which is much, much larger. And that it automatically makes it bad.
And external lines are not charged. I would agree with you if external lines were charged. This is not
okay. I guess we have to give the others chance for the answer for the questions first, and then.
This is a nice thing though, but we can talk about that later.
Okay.
Okay, thank you. Any other questions?
I have a.
Yeah, sure.
The first thing is a comment about what Igor was telling now. And the thing is that at each vertex, you have a conservation of form momentum. Then if the form momentum is large outside, it will imply large momentum inside. Then you have to be careful with the lowest Landau level approximation, even if you are only considering high momentum for neutral particles.
Exactly.
And the other thing is, well, was a question very related with the first one that Igor was doing, that what you have found is that a very strong magnetic field will affect only the longitudinal modes. But still you have the transverse modes. It doesn't mean that you don't have transverse modes. The only thing is that the magnetic field is not affected. Then how you are going to take the two contributions in the results?
No. What I showed is that when you consider strong magnetic fields, the tensor structure that emerges from the matrix element is a longitudinal structure. In other words, longitudinal everywhere, as it's shown in this.
This is clear. This is clear. Right. The question is,
so it's not that I am putting it by hand, so to speak.
No, I know. But what is the meaning of that? That you don't have transverse modes?
No, it means that for the large magnetic field part of the calculation, only longitudinal modes contribute. That's what I'm saying.
Contribute to the magnetic
to this process. I'm not claiming that this is the whole physics. To this process within these approximations.
It will mean then that the transverse modes disappear, or
No, Efrain, I cannot claim that. What I'm telling you is that within this calculation, within these assumptions, which means this Landau levels contribution in the triangles, these are the modes that contribute. That's all I'm saying. I'm not telling you that the others won't contribute. That calculation has to be done.
The other one, yeah, we are not going to feel the strong field, but I think they are going to be still there, and you have to take into account their contribution.
Efrain, what I'm telling, again, let me try to rephrase myself. What I'm telling you is that within this approximation, this is a structure that emerges. It's not that I'm ignoring the other modes by hand. This emergence is born out of the calculation. Now, if you don't have such assumptions, simplifications, probably some other modes will appear. The other two modes will appear, but that has to be done. There is no way that I can promise you that there will be or there won't be. There is no way. It has to be done.
It's only a problem of interpretation. No, what is the meaning of this result? And I was thinking that it means that if you have a very strong field, it can only affect the longitudinal modes. That's
probably, and we know, we know that, for instance, for the two-point function, this is the case. For the very strong magnetic field, you have only the longitudinal mode. And there, the physical picture is also clear. It's the only way that the color charge can push forward to quarks, which are electrically charged. That's true. Here, I don't have a physical picture yet, but it may be very, very much related.
Okay, thank you.
Okay, I think any other questions or comments?
I have a question.
Sure. Who are you?
Anna, hi.
I'm Anna.
Anna.
Hi, Alejandro.
Hi.
You should let yourself seen.
Yeah, it's a bit messy here, so it's okay. Can you see me?
Yes, I can see, I can listen to you. And yes.
Hi. The conditions, these restrictions you get for the phase space, you had to impose some restrictions in the magnetic field, right? I mean, constant and. But then later you relaxed these conditions, but I mean, later you calculated the magnetic field considering it's changing in time. Is
Correct.
it consistent, or, I mean, because first you consider it as constant and then you relax this. So,
right.
And this is important. I mean, it's not just a correction, because you could do these calculations because of these restrictions in the phase space.
Yeah, that's a very good observation as well. What I am assuming is an sort of adiabatic evolution of the magnetic field strength with time. In other words, it is easy to think that you can do the calculation for an average value of the magnetic field during its lifetime. And then just put a single value of this magnetic field and a single value of its lifetime, and then say, well, okay, this captures the essence of the calculation. Another way of doing it.
Yeah, I mean, no, this is fine. The problem is that in your slide, on the previous slide, you got restrictions for your phase space because of this, together with conservation of. I mean, you get that the gluon and the photon have to be collinear because of this, right? I mean, this is necessary to have this condition that the particles are collinear.
Right. No, the particles are collinear independent of the strength of the magnetic field. This is just
the next slide, maybe the 18th.
That one?
Yes. Yeah, you say, right. Because the magnetic field is constant and especially uniform, it cannot transfer form momentum to the gluon's photons. So if it's not constant and uniform, you can transfer momentum. Right,
but what I mean constant and uniform in space is that it is not varying with time. It is true that otherwise, if it varies with time, it will transfer energy momentum. That is correct. Now, what I'm trying to tell you is that, and this is a strong assumption, of course, there are two ways of doing the calculation. One is having an average momentum, and then using this average momentum to represent the full evolution. True. The other one is this adiabatic expansion. It's weird, it's true, but it's the same happens when you analyze the evolution with temperature of thermal systems. You all the times assume that if the temperature changes, then the change is adiabatic. In other words, that you let enough time, gave enough time to the system to relax. This is a very strong assumption. I agree with you. No question about it. Because otherwise what you're saying is that because of the change of time of the with time of the magnetic field, then of course the collinear propagation is not going to be anymore true. And this is actually a very interesting question, because yes, you see the change in the dispersion properties, the fact that there is a given angle of between the particles that are involved needs to come precisely from the exchange of energy momentum of the external particle, of the external magnetic field with the gluons. And that can only happen through a modification of the dispersion relations, because the field is not constant in time. That's completely true. As you can see, this is a theoretically challenging problem. My practical perspective in this matter is, first, let us see whether or not there is a hint that this excess photon yield can explain something. And then let's try to see all of the other details, particularly this one. This is a theoretically challenging problem, but I believe that it may be very interesting to find what is the modification to the dispersion properties of gluons in an evolving with time magnetic field. Completely.
Yeah, okay. And I have another question for you and actually for the audience. Is it possible that the magnetization of the medium, or I don't know, other effects like vorticity or whatever, make the field last longer, and then there is room for this thermal contribution, thermal and magnetic contribution, or it's just...
There may be more qualified people in the audience to answer this question. Let me just take advantage of the fact that I was the speaker to give you a short answer. There are calculations where what you do is to resort to think that the medium has a large electrical conductivity.
Mm-hmm.
So if that's the case, then when you put something to swirl, it'll keep swirling, and then it will produce that the magnetic field is enhanced, or at least it remains at a certain value of its strength that will allow you to think that its effects are felt even in the thermal phase. Now, these calculations, although it's fair to say that there are calculations that show that the conductivity is not that large, there is also an extra effect. This is an explosion. So the particles, on top of being swirling, they also blow apart from each other. So this also reduces the effect of the magnetic field. In other words, in my opinion, but this is, again, not just an informed opinion, but an opinion nevertheless, is that this is difficult. In other words, that making, at least for the largest energies, making the magnetic field and the thermal phase to be together is perhaps not very likely.
I mean, because even if the magnetic field is small, if it opens a new channel, then the temperature can be the dominant scale. So, I mean, it's just, I mean, the work of this magnetic field is just to allow diagrams that could not happen if the magnetic field is not there. And then
Correct.
The temperature is the high scale that will, you know, enhance this. Is it, that's what I want to know, if it's possible, or if it's...
I think it is possible, provided that the thermal phase kicks in when the magnetic field has not died out. And this, I believe, could be the case for smaller energies. But for the highest energies, it seems unlikely. That's my point of view about this.
Thank you.
Okay, thanks. So Masoud, do you have any questions?
Yeah, I wanted to actually to make some comments, and it is related to the questions. And I want to make actually 3 comments. And first of all, I want to make a comment about the uniform magnetic field. Actually, if you are assuming that there is something like a magnetic field that is a classical object that doesn't receive any back reaction from the fermions or other things, your theory, it must be the case that the time scale of, for example, the quantum processes that are happening in presence of magnetic field must be much smaller than 1 over the square root of the magnetic field. Okay, if that is not the case, then you cannot even talk about the external magnetic field. So whenever I think in quantum field theory, in presence of magnetic field, or in magnetoaerodynamics, or everywhere, wherever we talk about the magnetic field, we are a priori assuming that that is the case. Okay. This was my first comment. And the other comment was about the suppression, I mean, the magnetic field and the electric conductivity. It doesn't seem that in the quark plasma phase, the electric conductivity from lattice Q series about, let's say, as of order of 10 MeV, which is not actually very large if you compare with the lifetime of the quark-gluon plasma. So essentially, it doesn't make a contribution to existence of magnetic field after the hydrodynamization, not the normalization. But something that is missing, I think, is that we don't know a lot about the pre-hydrodynamic medium. We don't know, for example, we don't have any idea about what is its electrical conductivity or things like that. So, for example, I think your URQMD simulation and the other ones are essentially done in vacuum, yeah?
Right, it's billiard balls, yeah.
Yeah. So this is actually the question, because we don't, this is not actually happening in the vacuum, but it's happening in a medium, but we don't know much about that medium. Maybe that this kind of things can help us to learn more about that medium. And essentially we have something, we only have a bond, as far as I know, on the final magnetic field that comes from the lambda hyperons. That is about, EB is about 10 to minus 3 pounds mass squared. But if, for example, if we do a magnetohydrodynamic simulation that comes from some initial time and an initial value for the magnetic field, we don't know what happens in between. If the ideal MHD is the case, then that B0 must be much smaller. But if it decays faster, it means that the initial magnetic field at hydrodynamization time must be much larger than we found from the feeds to the URQMD results. I mean, we are very ignorant about what is happening to magnetic field in the earlier stages. Sorry for the long comments.
Right. Let me take the opportunity to try to address some of your the points that you raised, because I think that all of them are very interesting, and the continuing efforts on trying to pursue these questions will eventually result in a better understanding of what is the kind of matter that is created in these collisions. That's for sure, and I think this is the motivation that have all of us here discussing these topics. So to start with one, the last one, for instance, it is true, but on the other hand, the only way you can have a handle on the properties of these initial stages is to try to isolate things that one believes or that there are clues that let us know that these ingredients are only present at the early stages. And therefore try to access probes coming from those stages, interpreting their properties and relating them back to these early stages of the kind of matter created. See, this is what motivated us. We tried to identify something that was present at the same time. And this is lots of glue and a large magnetic field from our point of view. Why not quarks? I think Igor mentioned that at the very beginning, there are very few quarks. So, or at least there are more gluons than quarks. So in that respect, I think that it is important to identify the probe and to link it to some physical aspect of that can explain the probe. Now, let me jump to the first comment. You're absolutely right. What we need to do in order to think of an external classical field is to compare its flux with the elemental quantum of flux. And so for these systems, when this number is large, then you are at least well off, not necessarily in the safest of the grounds, but at least well off. And so one can do these calculations in sophisticated, a bit more or less setting. And it usually happens that the quantum of flux happens to be a number which is between 1 and 10. So in that sense, it's not a bad idea to think of this field as an external one. It'll be, of course, much better to have 10 to the 23rd or something, but it's not the case. The area, the transverse area is small. And even if the magnetic field is large, compared to the elemental quantum flux, is not, this product is not very large. But it would have been a pity if that was less than 1. Otherwise, this doesn't have any sense. But at least I think that with this in mind, we are more or less in safer grounds. Now, your second comment, if you may remind me, this was about hydro?
I think about electric conductivity.
Yeah.
Electric conductivity. Yes. Again, you have to be. One has to be careful. Of course, Lattice has nice results, and many colleagues have nice results. But this is always a competition between the properties of the plasma, the properties of a static swirling plasma versus a swirling expanding plasma. This is that doesn't live very long. On the other hand, so no, it's not clear though whether or not this conductivity calculations is a lower bound or what is it. In any case, it's small, and when you add on top of that expansion, it seems complicated to think that the magnetic field is self-sustained.
Okay. So I think now we have more questions than answers. I think the subject is very interesting and very exciting, and I hope that we can continue to think about this and to work about this all together. And I would like to thank again Alejandro for coming and for giving this nice talk. And I also thank all the other audience for coming and for including to this to questions and answers and the discussions. Okay. Thank you
very much, and I look forward to the next
again,
discussion.
Thanks, Alejandro.
Thank you, everybody.
Okay.
Thank you, Alejandro.
Thank you, everybody. Yeah.
Thank you, Neda. Thank you very much for organizing this.
Thank you, Alejandro. Yeah. Mm-hmm. Okay.